All right, so chapter 4, this is the third in our lecture series, and what we're going to do for you today and for our viewing audience is to introduce chapter number 4, which is on page 53. So the chapter is entitled Energy and Matter. So energy is that thing that we study where we say it can't be destroyed, but it can be converted. So what are some of those energies that we convert? Well, we convert electrical into mechanical. We can convert heat into locomotion. And so that's what we mean when we say that energy cannot be destroyed, it can only be converted. And matter is what things are made up of. And so we need to look at this. Why? Why is energy and matter important in HVAC or refrigeration? Well, refrigeration definition is this. We take heat where it is unwanted and we put it somewhere it doesn't matter. So what do I mean when I say that? What I mean is, take this room. Let's say it's humid in here, it's warm in here, and I don't want to be in a room that's warm or humid. Most of your customers will not want to have that either. So what we're going to do is we're going to design a system using a refrigerant that's going to absorb the heat in this room, and then it's going to move it in that refrigerant to the outside, and it's going to discharge that heat in the outside. And we're going to do this through a fluid medium that is called the air that we breathe. That's where we remove the air from, and that's how that's the heat exchange that's going to go on for the most part. So that process of heating is the energy, the discharging of the heat energy, and what happens to that fluid, to the air, is going to refer to the matter. So matter. This chapter, if you notice on page 53, has a gazillion key words. I'm going to go through those key words with you right now. So matter is going to be one of those key words. And matter has 3 states. Now, I don't mean Oregon, Washington, or North Carolina. I mean solid, liquid, and we're going to use vapor. Vapor can mean it's synonymous with gas, yes. But in HVAC lingo, we tend to use the word vapor rather than gas. But they mean the exact same thing. So your textbook, depending on who writes it, may use gas. But they definitely mean the same exact thing. You're absolutely right, Morty. Vapor, yes. Yes, absolutely. So all things in matter, that's what we're made up of, can be in these 3 states. The one that we go to the most commonly to compare is going to be this chemical compound that you're all going to be familiar with, and it's going to be my chemical compound that you all know, H2O, right? 2 hydrogen atoms and 1 oxygen atom. And when you combine that compound together, what do I make? Make water, absolutely. Now, water also happens to be the world's oldest refrigerant. And it has for like Mike, you'll know, when you go to the store, that specialty store for refrigeration equipment, to the wholesaler, you want to go buy a container of refrigerant, a jug of refrigerant, usually they say R410A, right? You've heard them say that. Well, H2O water has a refrigerant number. It's R718. So, and we use water as a refrigerant. We use water as a refrigerant, as what's called a secondary refrigerant inside big buildings in Manhattan. We don't have a ton of refrigerant vapor, refrigerant liquid flowing throughout that entire building, those skyscrapers, but we have treated water. So we cool the water, or we heat the water by absorbing the heat in the room, and then we remove the heat from that water. So I'm bringing this up because I want to get a base level for our science piece here. So we're going to look at this refrigerant for just a moment. So R718 water at 1 atmosphere and at 75 degrees Fahrenheit. First off, can anyone tell me what 1 atmosphere means? Definition of 1 atmosphere. 1 atmosphere means the weight of the air at sea level. The weight of the air at sea level. So 1 atmosphere equals 14.7 pounds at sea level. So that's considered, you can say, 14.7. A lot of times technicians will round that to 15, or you can say 1 atmosphere. Later when we start talking about a vacuum, that's going to be important because it really explains what we talk about when we say we're going to vacuum a system. What it means is that we're going to take the pressure inside that sealed container to less than atmospheric pressure. That's what a vacuum is. So 1 atmosphere, 75 degrees Fahrenheit, also significant because we're going to give this a name. We're going to call this standard condition. This is going to be called standard condition. We need standard conditions when looking at mechanical refrigeration systems because we need a standard. We need a point of departure to be able to compare other things to other things. So that we have many refrigerants today. Back 20 years ago, just a little bit further, it was pretty much, it was an R22, and then maybe for a while before it was an R12, and that was pretty much it. There may have been one for commercial, but there wasn't a lot. Today, the numbers of different refrigerants that come out on a daily basis is really difficult to keep track of. And so you have to make sure you monitor the internet or subscribe to refrigeration news just in order to keep pace with that. So there's a lot to keep track of. This year, I noticed a new refrigerant developed by Daikin Corporation, R32, is out there, and it's making has a big appeal. And if you read the trade publications, you see a lot of information about R32. I bring it up because I'm going to introduce it to you. So standard condition, we need that in order to compare things. So what are we going to compare? What about R718? Well, let's take a look at R1718 at standard condition. This refrigerant of ours, compound H2O, and let's do something to it. Let's either add heat or take heat away from it to see what changes with its state of matter. So let's see what that does. So if we were to look at heat, I have a question for you, and it's going to be this row. Someone guess, what's the difference? Is there a difference between heat and temperature? What do you guys think?
Yes.
Okay, I like that. Yes. Yeah, okay. Would you care to say what?
Temperature is a measurement of heat or the lack of heat, and heat is only looking at the inside of things.
Okay.
High temperature. In temperature is measuring the core and the heat.
Yeah, it's measuring, yeah, you're all on the right track. Did you guys on this side want to add anything? So temperature is a measure of the intensity of the heat. So if it's in Fahrenheit scale, it all has scales. So how will we know what the temperature is? When we wake up and we turn on News 12 or we turn on the radio, what do they tell us? Today's weather report, right? It's going to have a high today of or a low today of. That's the measure of the intensity of the heat. So this is going to be a measure of intensity. And as we measure things, it has different scales. And that scale has graduations. So, you know, we know 32 degrees Fahrenheit is freezing, and 100 degrees Fahrenheit is very, very warm. So we're going to look at different scales and different intensities of heat, because that's one of the things that we need to do. But what about heat? We said temperature and heat really are two different things. So heat is related to density. So I can have a block, need a block, no blocks around here to have today. If I have a brick, imagine a brick, and I heat that brick to 300 degrees Fahrenheit, and I throw that brick into a swimming pool, Olympic-sized swimming pools, to make sure the pools are the same size. Am I going to raise the temperature of that water with that? Probably not. A lot of water in an Olympic-sized swimming pool. And even though that brick, if you touch it, it's going to burn your hand. It's 300 degrees Fahrenheit, that's hot. But it's still not going to make much of an impact in that pool of water. Now, if I take a brick, and it's the size of my car, and I heat that up to 300 degrees Fahrenheit, and I throw that into a pool, Olympic-sized pool filled with water, I got a good chance I'm going to raise the intensity of that water, the temperature of that water, by a few degrees, because that's a lot more what? Heat. So heat is related to density of an object. How much heat it can hold is what we look at heat. So we have a whole other measurement of heat that we use, and it's abbreviated. You've heard it a million times. It is capital B, lowercase t, lowercase u, called BTU. It stands for British Thermal Unit. And that's a measurement of heat. So we're going to be looking at that correspondence of temperature and heat into different refrigerants. Because that's how we want to remove the heat from this room. We want to remove it from the heat from the air in this room as cheaply and as quickly as we can. So we design systems in order to do that. So, any question about the difference between heat and temperature? I'm going to show you where I was going with this, just so you have an idea. So now, I'm going to do a little bit of X and Y going on here. So I got my graph. This is going to be measuring temperature. So temperature goes up when we go up the scale. This is going to measure heat. And as I go out this way to my right, the heat will increase. And if I go this way, the heat will decrease. So now I'm going to look at water at 1 atmosphere to see what happens to it when I add heat to it. So this being 0 for everything, 0 temperature, 0 heat. We'll call it absolute 0, even though absolute 0 is a theoretical number. So at 0, I'm going to put another number, 32 degrees. At 0, the 32 degrees Fahrenheit, this is all on the Fahrenheit scale. The scale here is BTUs. As I slowly go from 0 to 32 degrees, I have a block of ice. But as I begin to add heat to that, which is what I'm doing in this direction, this is a solid. Now, as the temperature goes up, where it's going to max out at 212 degrees Fahrenheit. Why did I pick 212 degrees Fahrenheit? Yeah. That's where water begins to boil, right? So that's where water begins to boil. So it's does it begin to boil at 212 degrees at the Dead Sea?
No.
No. Okay, why?
It's filled with tons of salt, which changes the boiling point.
Well, go ahead.
The pressure at the bottom, you say the bottom?
Yeah, the pressure, the elevation is below sea level. Matter of fact, it's about 800 to 1,000 feet below sea level. And so you don't need as much heat, temperature, in order to start that water from boiling. No, it's the opposite of what it is. You need more heat than 212 degrees to make it start boiling. But if I'm in Denver, Colorado, this row right over here, I'm at who's my fans for sports here? Can you throw a football further at the Denver Mile High City? Right? It's 5,000 feet up in the air is the elevation of it. So is the atmospheric pressure 14.7 pounds? No. It's a mile up. So water's going to boil at a lesser temperature because pressure and temperature are going to be highly correlated. So, and that's why I started with standard condition, with comparing things, because if you were to go and work at Denver as an HVAC worker, you would have to take your gauges that you use and adjust them for the change in atmospheric pressure so that you would get correct readings. So I added heat in BTUs all along this right here. As the temperature increases from this point, I'm going to slowly continue to add heat until I've added 970 BTUs. Drawing's not the best, but here we go. That at this point, solid, liquid, and now it's going to be the steam, or what we call the vapor. So the temperature and the heat are two different things, but they are highly correlated. So now, if you've ever boiled water, you probably didn't realize this. Once you reach the intensity of 212 degrees Fahrenheit, you do not have a change in temperature until that change of matter is completed. So once you've done that, once you reach that boiling point, the temperature will not go higher than 212 degrees, even if you keep the pot on the stove with the flame turned up the same amount. It doesn't go to 300, for example. It only will increase when all of the liquid has been boiled off. And then it's going to make that pot very hot. So if that's how we get something to boil off, then if we go in this direction by removing heat, we get the reverse to happen. And that's what we do in air conditioning. We take our refrigerant, we absorb the heat in this room, and then we take it to a condensing unit. These things you see right here, here, and we release that heat to the outside.